Yeah. Yes. Yeah. I just gave a presentation 2 hours ago for the IRP meeting. They're busy with the IRP meeting. Yeah.
Cool. Yeah, that's what I understand.
Bao. Yeah.
All right, we're going to get started with this week's seminar speaker. Welcome back from holiday, everybody. Hope everyone had a good break. We're going to be kicking off this semester's seminar series with Dr. Han Bao, who was recently graduated from Dr. Dinh's group here at NC State University. He graduated in October of 2018. He's going to be heading to Idaho National Labs for fun and excitement in Idaho. His talk today is going to be on machine learning application and the optimization of system thermal hydraulic simulation. And with that, I'm going to hand it over to our speaker. Thank you very much.
Thank you, Dr. Shannon. So, just like Dr. Shannon said, next week I will go to Idaho Falls to continue my career there. So it's my honor to be the first one for the department seminar because I can represent my work to the whole department before I leave. So it's an honor. Okay, let's start. The topic for my PhD is a machine learning application in the optimization of system thermohydraulic simulation. So when we start the slides, everyone can ask a question at any time if the slides make you confused, so we can explain it at any time. All right, let's go. So I think this world is created by the dreamers and the lazy people, because before we go to work, we need a long time to be trained, to learn, to practice. So some people start to think about why not let machine to work instead of us. So that's why the machine learning and artificial intelligence happens. So that's how the machine learning and artificial intelligence change our life. Driverless car, we don't see any driverless car in the street right now because of some regulation rules and licensing things. But we can see the Go and the chess because we know that the AlphaGo just beat the ranked #1 player in the world. And also for the video games, we found that we can never beat the bots at all. It's very difficult, right? And also for the image recognition, the machine can recognize our friends or our family much better than us, even we have known them for a long time. So that's a surprise for us. When we go to the machine learning, there are 3 types of machine learning technique. The first one is supervised learning, including the classification and regression. So we can use it for the image classification or the cancer diagnosis or marketing, forecasting to make money, and also the data-driven modeling for our research work, which is much meaningful than making money, right? And also the other type is unsupervised learning, including the dimensionality reduction and clustering. We can use them for the data visualization and also customer segmentation. The last type is the reinforcement learning, such as game AI, or it can help us to make some real-time decision. So machine learning is a very hot topic in the world. As a nuclear guy, I'm thinking whether we can use machine learning to improve our own work. I think everyone has that thought. So, but because my work is based on the thermohydraulic simulation for the nuclear power plants, so I'm thinking about how to use machine learning to help the simulation and modeling for the real plants. And as we all know that there are some difficulties for the system thermohydraulic simulation because the world is complex. we have different components. We have multiple dimensional, multiple skew, and multiple phase phenomena in the transient scenarios for the nuclear power plants. There are so many phenomena. Some of them we have not fully understood. So it's very difficult for the people to model and simulate every details in the nuclear power plants. And we know that there are some ideal approaches to explore and predict the behaviors in the plants. The first one is that, okay, we can build many full-scale facilities to do the experiments. So we can use the experimental data to develop different models. Then we can use these models to make a code and simulate the plant. But actually, it's not easy to build so many facilities because there are so many phenomena we need to know. People can never. It's not affordable for the people to build so many facilities. So there are another way, another ideal approach which is called direct numerical assimilation, where the local information can be fully solved accurately with very fine mesh, but it's computationally expensive to deal with the system simulations because we have so many components and it's a long-term scenario. So people start to use some scaling methods to design different scaled facilities. So we can have different facilities for different phenomena, and based on the experiments, using these facilities, we can generate different models, and then we can integrate all the models and make a code and use this code to go back to simulate the full-scale prototype processes. But we know that there are some problems generated. The scaling issues, because this one is a full scale, but we need to scale down. And there are some uncertainties generated during the scaling. And the second part is the information is lost during the experimental, during our transfer, during the transport from the experimental data to the models. And normally we call it model error. And also the model inconsistency and the numerical errors during the application of the codes. So that's one of the motivation that's one of the motivations to use machine learning to help us to deal with all these problems, because it's not easy. So there is another problem, the lack of validation data. Because before we are trying to use the code for the modeling and validation, modeling and simulation, we need to make sure that this code or this model is accurate enough for our prediction. That's why we need generate some validation data to validate the code first. But normally, the validation domain is much smaller than the application domain, because no matter how many experiments you have made, or no matter how many cases you have run, the application domain is always larger, because if we only change the little bit on the geometry or on the boundary condition, the application is totally different from the case you have. So that's another motivation that, okay, we are trying to think another way that maybe we can just enlarge the validation domain a little bit so we can have more confidence and for the prediction. And that's what machine learning can help us. All right, just like what we mentioned before, we already have different codes for the system thermohydraulic analysis. We have lambda parameter codes such as RELIVE 5. Some of you may have some experience about it. And also the CFD codes such as STAR, CCM, Plus, and also some coarse mesh CFD-like codes such as Gothic. And all these codes are playing a game to make a balance between the simulation accuracy and the simulation efficiency. So people have to make a choice about between the accuracy and efficiency. But we are adults, we want both. So that's why we need machine learning to help us to improve the code, to estimate the error from the code. So when we have a target we need to simulate, we need to decide which kind of mesh or which kind of model we should use for them. Normally we make a decision based on our experience, but normally it's wrong. Our experience is wrong. So we go to find some experts about this code and ask them, okay, which mesh or which model is good for this case? They may give an answer, but they're not sure either. So we're trying to find another way that we can directly learn from the data and let the machine learning to give us an answer about how to estimate the simulation error and how to give a smart suggestion of the mesh and the model selection. And I have developed an optimized system, which is called Optimal Mesh Model Information System, OMIS system. And this data-driven framework can help us to estimate the local simulation error using machine learning and also give some suggestions on the selection of mesh size and model. So we can let these coarse mesh, low fidelity simulations to achieve the accuracy comparable to the high fidelity data, such as DNS or high resolution CFD. So here we have two questions. The first one is how to estimate simulation error by using machine learning. And the second one is how to suggest on the best selection of mesh and model. Let's go to the first one. Just like what we mentioned before, if we just change a little bit on the geometry or on the boundary condition, the prediction is totally different from our validated cases. So that will confuse people. And all these changes on dimension, geometry, boundary condition, or non-dimensional parameters can be considered as a change on the global characteristics on the target case, because it's not in detail. It's globally defined. But when we go to the detail, we may find something similar. For example, for different types of plants, we have different light water reactors, such as boiled water reactors and pressurized water reactors. No matter how the boundary condition or geometry changes, the game inside the core is always the match between the liquid and the vapor. So we can find the similarity there because it's always steam, it's always vapor and liquid. So based on the global characteristics and the local physical features, we can separate all the conditions into 4 types, which is called Gilli, and Gelli. And here I will use this piping flow example to explain all these concepts. Some of you may be very familiar with this piping flow. We assume that we have 5 cases here. The global physical condition is defined using a global Reynolds number with different values. And depending on the different values of Reynolds number, we can, according to our knowledge, we know that the local physics are different. For the low value of Reynolds number, it's laminar flow. For the high value of Reynolds number, it's turbulent flow. And between the laminar flow and turbulent flow, it's a transition between the laminar and turbulent. The local physics are different. So let's start from the Gilli, where the people will feel most comfortable, because the full name of Gilli is called global interpolation through local interpolation. For example, if we have the data from case 3 and case 5, and we are trying to use this data to develop a model and use this model to predict the case 4, we can find that the performance of this model is very good. It's as good as we expect, because no matter globally and locally, there's a same, right? It can be considered as an interpolation. No matter the value of Reynolds number or the local physics, they're very similar. So that's very good for us, for the researchers. So we can develop a model based on the existing data and use it for the prediction. But actually, in fact, this condition is just a much small part in the world. Let's go to the second part, GILI. The full name is Global Interpolation through Local Extrapolation. For example, if we have the data from case 1 and case 3, and we use this data to develop a model and use this model to predict the case 2, we can find that the model is not as good as we expect, because the local physics is totally different. The transition is not covered by the laminar flow or by the turbulent flow. So we find that even globally it's an interpolation, but if locally it's an extrapolation, then the prediction is not good. The existing data is not useful for the prediction of the target data. And the GALI has a similar situation, which is called global extrapolation through local extrapolation. So if we have the data from case 1 and case 2, and we use this data to develop a model to predict case 3, we will find that it's much worse than the other twos. Because no matter globally and locally, the physics are totally different. Okay, let's go to the fourth part, GALI, global extrapolation through local interpolation. This part is what we try to focus on. Because, for example, if we have the data from case 3 and case 4, and use the data to develop a model, and use this model to predict case 5, we can find that even globally it's an extrapolation, but locally they're the same. So we can find that the model prediction will be very good, will be as good as we expect. So that's one way that we can enlarge our validation data, because we are not just focused on the global characteristics. We can go to the local physical features that can help us a lot. So in the piping flow example, we have explained the interpolation of local physics. But actually, when we go to the statistics, when we go to the data analysis, we can find another explanation about the interpolation of local physics. From the perspective of data characteristics, because we can find we can identify a set of physical features, local physical features, which can represent the nature or the pattern of the local physics. So if we can find the similarity between the local physical features of training data and test data, we may find a way to bridge the global skill gap. Okay, you can ask questions at any time. So that's a way to bridge the skill gap by exploring the local similarity in the Gallic condition. Yeah, so that's the answer for this question: how to bridge the global skill gap by exploring the local physics in Gallic condition. Firstly, we need to identify different physical features and build trained data and use machine learning to find the natural patterns inside data. And this chart is a central idea of this data-driven approach, because in the beginning we just know that the simulation error is influenced by the physics of interest, by the model error, and also the mesh error. But because the model error and mesh error are connected by the mesh size, they cannot be estimated separately from each other. So we are trying to define some physical features, which also consider the physical parameters, the model information, the mesh size, and then we use machine learning to explore the relationship between the simulation error and these physical features. That's the goal of this data-driven approach. If we can find the relationship between the local physical features and the simulation errors, then we can just insert the values of physical features for a new case. Then we can have a good prediction on the simulation error for that new case. Okay, the next step, the first step is to identify the physical features. As we said, we need to consider 3 factors here: the mesh size, the physics of interest, and also the closure models applied. So there are 2 types of physical features considered here. The first is the local physical parameters, which includes the physical non-dimensional groups and also the parameters involved in the closure relationships. And this part enables this data-driven approach, the scalability and the additivity of physics. For example, in the beginning, we just consider a very simple case as a friction. We can define some physical features for this friction. But when we go further to the turbulence, we can still use the physical features defined in the friction, and also we can add some new specific physical features for that turbulence. And of course, when we go further to the convection, we can define some other physical features which are related to the heat transfer. So that's the first part of the physical features. The second part of physical features are the gradients of variables, including the first order derivatives and the second order derivatives. We use these gradients of variables. Okay, the variables are the quantity of interest, such as the velocities, the temperature, the pressure you care. Okay, so the reason we are using gradients, not only the value in the local cell, because that the gradients can include the regional information, not only just one cell, but all the cells. We can imagine like this. In the beginning, we just have a data from a small square control volume. And we need to predict the case in a large round control volume. It's not easy. But if we find that part of the large round control volume is very similar to the small square control volume, then we can use the information from here to inform the prediction here, right? Because they are similar. We don't have to consider globally. We can just focus on the local information, the local physics. So if this can be done, so if the prediction on this part can be informed by the information from this square control volume, we can just imagine that if we have like 10,000 small square control volumes, we can inform the other parts inside the large round control volumes. We don't need the code. We just need the data, right? So that's a way that we can purely rely on the data, not on humans' knowledge, because human knowledge sometimes make mistakes. But if we just rely on the data is much trustable than people. All right, so here is a workflow for this data-driven approach. In the beginning, we need we need to train the error function, because so we need to generate the high fidelity data based on some very fine mesh codes. And also we need to generate the low fidelity data from the low fidelity simulations. For example, we can use some coarse mesh nodalization as a low fidelity simulation, and some fine mesh nodalization as a high fidelity simulation. And so by comparing these two simulations, we can find the error between high fidelity data and low fidelity simulations. And the physics features are totally defined based on the low fidelity simulation. Once we build this training data set, we can use machine learning to train the data and get an error function whose inputs are the physics features and outputs are the simulation errors. And next step, we need to test this function. So we need to some more data about, which also includes the low fidelity simulations and high fidelity simulations. And we just insert the new values of these physics features into this function, and then we have a predicted simulation error, right? By adding this simulation error on the low fidelity results, we can have predicted values for the high fidelity simulation. So next step, we need to compare this value and see how much error the machine learning brings to us. And if the machine learning error satisfies the expected accuracy, then we can use it for the further application. If it does not satisfy the accuracy, we need to go back. Maybe we need more data for training. Maybe we need more physics features. Maybe we need a much better machine learning algorithm for the training. That depends. So that's workflow and information flow for this data-driven approach. Okay, next step. Next, we're going to a case study, and Gothic, which is a coarse mesh safety-like code, is used as a low fidelity simulation. And the structure of Gothic includes the conservation equations, the source terms, and the closure models. And because our case study is about mixed convection, there are three closure models which we concern a lot: turbulence model, convection heat transfer model, and the wall friction model. We can by reviewing the manual and the correlations, we find that the mesh size will affect the calculations of the model errors, such as the wall distance, the local cell width, the hydraulic diameter, and the wall length. That makes the mesh-induced error and the model error are tightly connected. And the machine learning algorithm we are using for this case is feed-forward neural network, because compared to other machine learning algorithm, feed-forward neural network has a very good performance to dig the deep nature and patterns for people. And also, FNN has a capability of deep learning because we can add the hidden layers and also the neurons. So it can help us to learn from the data and generate insight from the low-level features to the high-level features. Okay, the case study is on mixed convection. And here we have three case studies: the extrapolation of geometry, the extrapolation of boundary condition, and extrapolation of dimension. And we also have some questions here, because as we know that if we have more data for the data training, normally the prediction of the machine learning will be better. But it's normally, because the similarity between the training data and testing data is much more important. That's our question. Okay, I just said the answer, but that's what we need to explore. And the second question is the relationship between the similarity and the prediction error, because we expect that if the training data and the testing data is more similar, the prediction error will be much less. And the metric for the extrapolative distance is defined as the mean KDE distance. KDE is the kernel density estimation. And the metric for the prediction error is defined as the normalized root mean squared error of variables. Equation is right here. Okay, case study 1. In the beginning, we just have this square control volume. We just have the data for this square control volume as data set A1 to A12 with different injection temperature and injection rate at the bottom. Because for all the cases, there is a hot air injection in the bottom and a cold wall with a fixed temperature on the top, and here is a vent. So the air will go inside and mix and go outside. All right. So this case is what we have for the training, and we are trying to use the data from this square control volume to predict the cases with rectangular control volumes. Here we have two types of rectangular control volumes with different aspect ratio. They also have the hot air injection in the bottom and the vent on top. So, okay, for this case, first we need to define and identify the local physical feature group. Just like what we said, we have two types of physical features, and based on this, so we have defined like 30 physical features for this case study. And all right, here is for this study we have 4 tests. The first is that we use all the square data for training to test the rectangular cases. And the second one, we just use part of the square cases from case 4 to case 10 to do the prediction. And third test, we just use the data from case 6 to case 8 for the prediction. And for the test 4, we are using the rectangular cases for the training to predict the square cases. Okay, then the first is to see the similarity between the trained data and test data. These red points are from the rectangular data. In the beginning, it's 30-dimensional, but we are using some dimensionality reduction technique to reduce from 30D to 2D, so we can have a visualization of this data. Here is so red points are from the rectangular data, and black points are from the trained data set from the square data. In the beginning, we just plot the rectangular data, and when we put the square data on the rectangular data, we find that most of the rectangular data are covered by the squared data. But we can still find some points here, and here. But most of the rectangular data are covered by the square data. So we can see that even globally, the geometry is different, but locally, they are the same because the data is covered. So that's why we have the confidence that even we only use the data from the square case, we can still have a very good prediction on the rectangular case. And here is the plot for the test 2. We just use the data from case 4 to case 10 as the trained data. We can find that even the trained data is much less than this one, but the testing data is still covered, is still mostly covered. And for the test 3, sorry, it should be test 3, we have less trained data, but the test data is still covered. So Okay, here is just results for the different tests. Because it's a 2D problem, we have two velocities, horizontal direction and the vertical direction. And we also have the temperature. The blue points are from the Gothic simulation, the cost mesh original Gothic simulation, which is compared with the red points, which are the machine learning prediction. The x-axis is these two data, original Gothic simulation and the machine learning prediction. The y-axis is a high fidelity simulation from StarCCM Plus, which is generated by using fine meshes. So if this point can locate on the 45 angle line, it should be good, right? So we can find that the machine learning prediction is much better than the original Gothic simulation. That's how this data-driven approach improved the Gothic simulation. So we can find that even we have less and less training data, the prediction is still very good. That's because the tested data is covered, right? Even we have less training data. Okay, so this is for so all these cases can be considered as Getty, because globally it's an extrapolation, right? We are using square cases to predict the rectangular case, but locally it's interpolation because the data is covered. So let's go to the test 4. We are trying to use the rectangular cases for training and the square cases for testing. So for this case, we can just consider that the testing case is locating in the Getty condition, global interpolation and also local interpolation. So we can find that the prediction from the machine learning is still much better than the original Gothic simulations. All right, so we can have a conclusion about this case study. Smaller KD distance, smaller extrapolative distance, we will find higher similarity between the training data and tested data. And of course, we will have smaller prediction error. And here is a case study 2, the extrapolation of boundary condition. In this case, we only have the geometry of the training case and testing case are the same, square. But the top heat transfer condition is different. For the training, the cold wall has a fixed temperature, but for the testing, the cold wall has a fixed heat flux. We are trying to use these cases for training and this case for testing. For the testing case, we have different heat fluxes on the top. So we can also find that for even globally, the boundary condition is different. It's extrapolation, but locally, the data is the information is still captured by the machine learning model. The prediction from the machine learning model has a much better performance than the original Gothic simulation, no matter for the velocities or the temperatures. But we also find some bad points, which are not as good as we expect. That's because when we go deeper to find where they come from, we find that they come from the top left part, because in this part, the heat transfer is underestimated by the machine learning and also the low fidelity data. So also in this case, we found that, okay, if we have smaller extrapolative distance, we can find higher similarity, and of course, we can get smaller prediction error. Here is for the case study 3, extrapolation of dimension. In this case study, we are trying to use some small control volumes for training and a large control volume for prediction. They have the same geometry, both square control volumes, and they have the same boundary condition, the cold wall with a fixed temperature. The only difference is the dimension. So the first thing we are trying to find whether the local data is covered or not. The four figures on the top are from the test data with different height and length from 1.2 meter to 5 meter. And the black points are from the training data. So we can find that for the testing case with a height equal to 1.2 meter, most of the points are covered by the training data. But for other cases, we find that the tested data is not covered. For example, for the case with height equal 5 meter, this part data is not covered, this part not covered, this part not covered. So this case can be considered as global extrapolation, but also local extrapolation case, which is called GALE. We give a definition, a classification here. So for this, for the first case, we put the results here for the testing data set 1.2 meter by 1.2 meter. We found that for this GALE case, the machine learning prediction is still much better than the original Gothic simulation. But for other GALE cases, the results are much worse. And in this case, we also find that if we have higher similarity, we can get smaller prediction error as a test one. But for other cases, the KDE distance is much higher, and then the prediction error is also much higher. So we know that for the GALE or GALE condition, this data-driven approach can work very well. But for the GALE case, it does not. Okay, so by introducing the whole data-driven approach, we know how to estimate the simulation error. First, we need to identify the physics features, and build the training data set, and use the machine learning algorithm to train the data, and then get an error function. And for a new case, we can just insert the values of physics features, and we can get the prediction on the simulation error. So the next question is how to suggest on the best selection of mesh and model for your target simulation. So here I just develop ARMY's framework to find out how to give a suggestion on the mesh and model selection. So in the beginning, we need to know our target. We need to know which component or which phenomena we need to simulate. And then we need to build some test metrics to evaluate our machine learning model. And then we need to make sure that the physics feature we have defined are sufficient enough for our prediction. And then we need to make sure that the machine learning algorithm we have chosen is good enough. And the step 5 is to make sure that the training data is very similar or very relevant to the prediction cases. And after all the optimization part, we can give a suggestion on the mesh and model selection. So because the time is limited, I will not give too much details about the framework. But for the case study, I can give some introduction. So if we still have a mixed convection case inside for a squared control volume, and we're trying to decide, we're trying to make sure, okay, which mesh size we should use for this simulation. Then first we need to know which kind of physics we are get involved, and which model we can choose, and which mesh we can choose. And second, step 2 is to identify the physical features and collect the data from high fidelity simulation and low fidelity simulation, and build a database. And we also need to make sure that the machine learning model we have developed is good enough for our cases. So we need to design a test matrix and test our machine learning model and make sure that it's good enough for the application. And step 3 is the optimization of physical features, because sometimes the physical feature is not sufficient enough. Sometimes there are too many physical features. Some of them are not as important as other ones, so we need to pick the most important physical features for our application. And step 4 is determination of the machine learning algorithm, because we need to make sure that we have sufficient neurons and hidden layers for our training. And we also need to make sure there are not too many, because it's computationally expensive. And step 5 is we need to select the most relevant data for training. And last, we know that which physical feature we need to use, which neural network structure we need to use, and which trained data set should be used as for the last application. And then we can make a prediction on the target case and check whether our suggestion is right or not. All right, so I think that's the end. That's all the work I need to show to you. In this work, I'm trying to develop a data-driven framework to estimate the simulation error and also give a suggestion on the selection of mesh and models. So I hope all you guys can take benefit from it, if possible. And here is a imagine of the future about the data-driven system simulation. Even when we have a very complex plant to simulate, there are so many phenomena inside. If we have data which is easily generated and very simple generated, but they can just represent part of the phenomena inside, then we can collect much more simple, easy running, fast running cases to generate a data warehouse which can help us to inform the real simulation inside the plant. In that way, we don't have to simulate the whole plant. We just use the data with fast running codes and easy modeling cases. So, yeah, that should be much easier. And the uncertainty from human beings in the selection of mesh and models can be ignored. Okay, so that's all I need to show. Thank you. Any questions? All right.
Why going from rectangle to square is interpolation?
All right. You mean local interpolation, right?
Yeah. Why
Yeah, because okay, let's go back to that figure so we can explain better. Right. Yeah, right. Here, the training data case from the square control volumes and testing case from the rectangular cases. So from the global geometry, it's an extrapolation, right? But if we go to the details, if we just plot the local data, just like the points we showed here, we find that these red points, which are testing data, is totally covered or mostly covered by the training data.
So you are defining the condition after you get the results or before? You are doing it before, right? Before you get
Yes. First, we need the data. We need to run the cases. Yeah. Right. All right. Yeah, I just look at the faces, which I shoot during other seminars. So yeah, I can. Yeah, that's fine. But if you don't have any questions, that's fine. But I hope this presentation can let you start some thinking about how to use machine learning in your own work, because even my work is about thermohydraulics. Maybe some of you are not relevant to thermohydraulics, but the application should be the same. We are doing the regression work. We are doing the data-driven model. We are doing the modeling work. We are doing the simulation work. They're the same. So, yeah, I hope it helps. Yeah. All right. Thank you. Thank you. Thanks.
So where did you say you're going?
Idaho National Lab.
Oh, cool.
Yes.
You're going to be working with Bob? Young
No, not Bob. Different department. I will go to the system integration department. The department manager is Shannon Bragg-Seaton. Yeah, you know her. Yeah. And because I went there twice for my internship, so they know me a little bit. So yeah, so that's why I have a chance to return there and continue. Yeah.
Good.
Yeah.
Well, congratulations.
Thank you. Thank you for listening.